everybody. Thank you for joining us today for the NVM Express hosted Powering the Data Center with NVM Express webcast. We're happy to have you here today. I want to take a minute to introduce our presenters. So you have Mark Carlson, who's a principal engineer at Toshiba Memory, and then John Kim, who is the director of storage marketing at Mellanox. And I'm going to go ahead and pass it over to the presenters now.
Thank you, Megan. Welcome, everybody. This is a webcast of NVM Express. Just a quick introduction. NVM Express is a nonprofit industry organization developing an open collection of standards and information designed to fully expose the benefits of non-volatile memory. In other words, helping you get more out of fast flash or other fast non-volatile storage. It's basically designed from the ground up to deliver high bandwidth and low latency, and we'll talk about some of that in today's webcast. These specifications, well, you can read more about the slide. These specifications make it easier for many customers and vendors to collaborate and standardize access and use and management, both locally and remotely, of fast storage. So I think we can skip some of the details on this slide, but it's all good information, and you can find much more about this at the nvmexpress.org website. Today's talk is about NVMe and changes for a modern data center protocol. It's about powering the data center with NVM Express. So as you probably know, the NVMe standard is evolving to support data center deployment of SSDs. So hyperscalers, meaning very large, well, we'll talk about that in a second, but hyperscalers have been bringing their requirements and their requests to NVM Express regarding things such as performance isolation, predictable latency, write amplification, better management of flash endurance, and so forth. And as a result, new features such as I/O determinism and predictable latency and endurance groups have been added to the upcoming NVMe 1.4 specification to help address some of these concerns. In addition, NVMe over Fabrics has added support for TCP as a transport and fabric. So in this webinar, Mark Carlson of Toshiba and John Kim of Mellanox, which is me, we will cover the issues and show the new features from multiple data center perspectives. So as we get started, just a brief definition of what we mean by data center. So data center means any organization that's building basically large data centers and populating them with modern scale-out components and modern systems. So first and foremost, we mean the hyperscalers. This could be 12 or 13 very large web customers who have multiple huge data centers, and they use very modern scale-out deployment methodologies and architectures in them. But it also means the tier 2 data center customers, which are other large web companies and large enterprises that are applying many of these hyperscaler techniques to their data center designs. Many of these customers specify their designs and the components they want, and they have ODMs or original design manufacturers assemble them for their data center. And in many cases, they use the Open Compute Project or OCP standards as a standards group as a way to develop a particular hardware standard or management standard, and then incorporate those into their hardware designs. So each of these hyperscaler or large data center customers tend to have unique requirements, such as for SSDs or management, but there are also common requirements for which standards can play a role, and that's where NVM Express Inc. has helped develop these standards and advance these standards in response to these requirements. And the good news is that the more standards there are, the easier it is for the drive vendors to comply with them and support them, because it means less custom code when you have more standardization. So that said, let me turn this over to Mark Carlson, who will now talk more about the use cases as well as what these new specifications and standards are in NVMe Express. Mark?
Thanks, John. Yeah, this is Mark Carlson. Some of the use cases include boot and log for OS boot drive, especially when you're doing a hypervisor and every customer has their own virtual machine. You want the OS and application logs to go into SSDs in some cases. And then there's the databases. DB and databases have a working set of around a terabyte and so the SSDs need to be sized. And then SSDs are also used for cache, either content caching or object caching or indexing through objects as well. So where do they use flash today? Well, there's all sorts of uses. You can put flash on server motherboards. This is a very common practice. It speeds up the multiple use of that system by multiple applications. They're also making storage systems, and in a lot of cases they're using the M.2 form factor. One of the reasons is that they're fairly small drives, and they match the working set of these databases and other applications, and they don't end up having multiple applications competing with the same resources. In fact, they're making M.2 drives into, plugging them into what are called carrier cards, and allowing higher density of M.2 drives in both their servers and their storage systems. So some of the characteristics and challenges, scalable, well, meaning it's scalable to a data center and flexible in that it can be repurposed for different tasks at different times. They fill their data center with SSDs, so they have a very high volume ordering SSDs in very large quantities, and thus they are driving down the cost of SSDs for everybody, really. Power and thermal efficiency is very important. They only have so much power and cooling in a data center, and as the drives get more and more advanced, this becomes one of the primary concerns. They want to be able to service them. They want to be able to hot swap, if not the actual M.2 drives, at least the carrier cards that they're mounted on. And they really care about things like performance per terabyte and quality of service, and we'll talk about this further, the long tail of latency. Somewhat less important for these customers is backwards compatible. They can change whatever they want in their data center. They have an installed base of stuff that doesn't necessarily need to migrate forward using newer types of drives. They also need support for non-volatile media with the maximal density and the peak performance is not so much important as removing this long tail, as I said. So the power and thermal efficiency, like I said, they have a data center operating zone where they like to stay. They don't want to have to move air faster across the drives. That costs more. And so they want to keep them in an operating zone, if you will. And so this operational expense, or OpEx, really matters to them because it's what they pay on an ongoing basis. And the managed NVMe allows them to control this and effectively manage the thermals. But they also need an interface that scales with capacity. So they want IOPS that when you get to the larger data sets can scale linearly like you're showing here, whereas something like a SATA interface really doesn't scale when you get to the larger capacities. So one of the things that is new for NVMe 1.4 is something called I/O determinism, and this allows you to take a larger SSD and logically break it up into smaller SSDs that don't impact each other's performance. So they're essentially isolated sets of media that can be used by separate applications without running into what we call a noisy neighbor problem, where if you have multiple apps hitting the same media, they can interfere with each other, cause long tails of latency and drop their quality of service for the reads that are going on. So we've seen some great numbers with I/O determinism as far as getting the quality of service of the read operations going. You see here on the left a chart where you compare one large SSD with a bunch of smaller SSDs, and you definitely do get quite a bit improvement in the IOs per second. And then when you look at the random read latency and the probability in getting these latency outliers, you see a big improvement, especially between sets and no sets when you get to these long tails of latency. And then we also have a new part of the standard called NVMe fabrics over TCP. And this allows you to take those NVMe SSDs and remote them to multiple hosts or clients. And again, this allows you to manage those smaller pieces of media over a larger number of clients, if you will, and that allows you to expand this going forward. So these are some of the common requirements that we're going to talk about in the rest of this talk. Tail latency is a big problem because it impacts the customer. The customer sees slower page loads. Parts of the page are loaded and other parts are still waiting to load. In a lot of cases, those parts are advertisements, and if you can't put those advertisements in front of a customer in a timely manner, you're going to have issues with those customers. The predictable performance is part of that, but we also need to understand that when you're trying to read a piece of media and you have problems reading it, there's all sorts of sort of correction steps that can be done by the drive to recover that data. And in some cases, sort of a heroic recovery. But that heroic recovery takes time. It takes a response in a matter of microseconds. And so we have introduced an option to fail fast, which would allow the application to get the data from a different drive that maybe doesn't have a media problem right now. The isolation aspect is where, again, you've got a noisy neighbor problem of many drives hitting a large capacity, and many apps hitting a large capacity drive and interfering with each other and causing these long tails as well. Another big concern is wear, and this comes down to cost. If the way that hyperscalers and other data center customers are using the drive causes it to wear out faster, they're not getting maximal usage of that particular media. So some host applications really need more control over what's called the flash translation layer, or FTL, and this involves wear leveling. They want to be able to wear level the pieces of media themselves. The drive does a good job without a whole lot of understanding of the app, but when you do understanding the app at a system level, you can be much more efficient as far as things like wear leveling. And then you need to control which pieces of the FTL are done on the host and which pieces are done on the drive, depending on what application is using it. And then lastly, we have TCP for storage networking, and John will dig further into that. So as we go through these, we'll check these off. So drilling down into I/O determinism, back several years ago, we had multiple hyperscalers come to the NVMe board of directors with an I/O determinism proposal. And over the next 2 years, we worked this out with their cooperation, and produced 2 ratified technical proposals that contain both the I/O determinism as well as the NVM sets and read recovery level. Those TPs are out and available to you now, so you can go look at those features. They're also being integrated into the upcoming 1.4 version. So what are NVM sets? An NVM set is one of these carved out collections of non-volatile media with particular attributes from which one or more namespaces can be allocated, right? An NVM subsystem supports one or more NVM sets, and you can discover those sets in the identify controller command. NVM sets are isolated from each other in regards to quality of service for I/O commands. For example, all the media can be on a separate channel on the back end, and that isolates it from media that's on other channels on the back end. But this is all done behind the scenes of the actual interface at this point. Now, one thing we did punt on for this first release was the creation and deletion of NVM sets. For this 1.4 release, basically the NVM sets are created at the factory as part of the drive configuration shipped to the customer with a design configuration. One problem with this is that if you have multiple customers as a drive vendor, and they each want different configurations, you have multiple SKUs, multiple tests, multiple qualification steps for each of those different configurations. I'll show how we solve this, or we're planning to solve it in the near future here. The read recovery level is something that I briefly mentioned, and this is the idea of failing fast so that you can go on to someplace else where the data is and not incur a tail latency. So the different levels of read recovery are how you do this. You set the level of read recovery that you want for this particular NVM set. And so there's some examples there of those different levels. In the example, uncorrected bit error rate, or UBER, that you would get as a result. The other thing we added to I/O determinism is these states. So you can put the NVM set into 2 different states. One is a deterministic state where all the background operations from the drive are held off, and you're giving full use of that drive just to satisfy the read request that you come in. But of course, the drive will build up work to do during this period, and so you have to give it some time in a non-deterministic state to work off this built-up work. It could include read patrolling to detect read errors. It could incur wear leveling and garbage collection. All those things are only allowed to happen during that non-deterministic state. So we give various parameters during these 2 states to help the host understand how much work needs to be done, how much more time it can spend in these deterministic states. So these are, we have a deterministic 4K, random reads, deterministic writes, and maintenance time. I mean, these are what are called reliable estimates, which means they're not hard numbers, but they're an indication. And when your deterministic 4K random reads goes to 0, means that you need to let the drive get into non-deterministic state to do some work. And at the same time, even if you're doing nothing to the drive, but still holding it in a deterministic state, that work will build up as well. That's the maintenance time. So you can imagine these are correlated and move together when you are actually using a drive, and that's what's shown here in this graph. So we've addressed the tail latency. through the isolation, through the predictable performance, through the windowing and the heroic and recovery levels. The way of splitting up a drive into separate NVM sets achieves the isolation that it needs. So let's look at the next set of things, which include wear management. Right?
Actually, Mark, Mark, if I could interrupt. There is one question that came in that's about the latency and determinism, so I'd like to give that to you now before you go into endurance groups. The question is SSD long-tail latency or non-determinism intrinsic to solid-state dies or solid-state controllers, or is it tied more to the communications interface such as SATA, SAS, NVMe, or PCIe?
It's not tied to the interface. In fact, we put in similar sort of recovery levels, for example, in SAS and SATA. But the idea of this background work that the drive needs to be doing happens both in SSDs as well as hard drives. Persistent memory DIMMs may or may not. A lot of the persistent memory DIMMs available today front the actual NAND with some DRAM. And this DRAM, then data needs to be dumped to the NAND at some point, but that's usually under power failure conditions or shutdown kind of conditions. It doesn't really impact the performance of the DRAM while it's operating. So really it is mostly an SSD. The SSDs have a lot more background work than a hard drive does, for example. So it is primarily SSDs.
Got it. All right, Mark, thank you. And for answering that, please go on.
All right. So let's talk about now endurance group management. Now, an endurance group covers what the drive is wear level. So in the first version of NVMe IO determinism, the endurance group was only set by the drive, and the drive would set an NVM set to be in one endurance group, but an endurance group could have multiple NVM sets in it if the drive is wear leveling across sets. But a more typical case is where the host is wear leveling across sets and the drive is wear leveling within the set. In that case, the NVM set and endurance group would be one for one. So we wanted to open up this and make it more controllable by the host. Thus, we were introducing this endurance group management feature. So the media unit endurance group management would typically be used with a drive, an actual SSD drive, and the operation would select from a fixed set of complete configurations, and then that selected configuration would be used for the lifetime of the NVM subsystem after it was installed. And this should satisfy the requirements of hyperscalers. They can configure their media units. A media unit is really just a piece of media that is wear leveled by the drive, kind of the finest granularity, if you will, of wear leveling that the drive can support. So you can incrementally configure endurance groups and in a system, but in a drive, this is the kind of the way that we want to use them. You pick a configuration, use it going out. It's just a one-time operation right up front. We also have something called capacity and endurance group management, and this is more for the system size NVMe system. They want to dynamically create endurance groups and NVM sets, and they really don't care about the pieces of media that need to be wear leveled. The system is doing all of that on its own, but again, it's over and above what the drive does down behind the system. So those are the two types, if you will. So for I/O determinism users, they need to create some NVM sets according to their requirements. Let's say they need 1 terabyte sets isolated from it. So here's an example of a 4 terabyte drive. The configuration would be to set up 4 NVM sets, each with their own endurance group, like I was saying. The drive is wear leveling within the endurance group, all dozen pieces of media. And then the host is wear leveling across the NVM sets to make sure the overall drive is wear leveled, right? But you don't have to go with 1 terabyte sets. You could do 8 half terabyte sets on this 4 terabyte drive as well. The channels there are shown so you know what the communication isolation is going to be. And then we have other use cases where the host wants to do all the wear leveling across the entire drive based on each of these media units, right? So what they know is they've mapped this media unit to a namespace, and everything they write within that namespace goes to wearing that particular media unit. And thus, they know the channels. They know which media units are on the same channels. They can do their own isolated I/O. They know when they're going to contend with each other for the same media unit or for the same channel. And they can manage their I/O to achieve low latency, predictable performance, etc. So we're basically adding the knobs to allow the host to configure the back end of an SSD in any manner that they want. So each of the media units has some information that refers to how it's going to be configured. Which endurance group is it part of? Which NVM set is it part of? Which channel is it on? Each of the channels on the back end is numbered. We also have the ability, perhaps in the future, to change the bits per cell on a media unit and adjust the capacity as a result. We also maintain, when it's not part of an endurance grouping set, how much of that spare capacity is still available on the media unit. And then also a percentage used that tells you how worn or how long-lived that piece of media can live, etc. So that's the details of the interface for each of those media units. And so when you actually specify, what you specify for a media unit is the endurance group, the set, and its capacity adjustment factor. So the storage system users, they need to basically just create, resize, and delete endurance groups within what's called a domain. And a domain is an overall capacity group in a storage system that has front-end controllers that will maintain it and access it. So a disk drive, a SSD, excuse me, would be essentially a single domain. But in a large storage system, you might have multiple domains. The domains can fail separate from each other, and so you need a bunch of interface to deal with that. So they're primarily tied to the TP 4009 that describes domains, but since they're proceeding in parallel and needed this capability, we put it into this feature as well. So capacity to create an endurance group is drawn from that domain, and then there's separate operations to create endurance groups and NVM sets. And also deletion of endurance groups. And every time you delete an endurance group, it's also going to take with it any NVM sets you put in there and associated namespaces as well. So this is the actual command to create endurance groups. The first value 0 type of command is just to select one of these media unit configurations that's typically going to be implemented by an SSD. So you pick one, you specify it here, you're done. Right? Of course, if you want to reconfigure it, you first have to release the previous media unit configuration, so there's a command for that. And then for the storage systems, you'll see there's a command to create and delete endurance groups, as well as to create and delete NVM sets. And these can be done individually as needed. So the entire feature contains commands for both types of use cases. So we see we've met the common requirements for where and for more control over which parts of the flash translation layer are done on the host and which are done on the drive. So I'm now going to turn it over to John, who's going to dig down into the TCP for storage networking.
Mark, thank you very much. Before I get started with NVMe over Fabrics using TCP, excuse me, there is another question I thought it would be good to have you answer.
Sure.
The question is, where is the overlap between NVMe solid-state storage and persistent memory DIMMs? What are use cases that might move this boundary between them?
Well, NVMe is a block interface. We are adding a key value interface to it. And persistent memory DIMMs have a memory or byte addressable interface. There are parts of NVMe, however, that are byte addressable, usually by a direct memory access controller moving the data in and out of NVMe drives. So there is something called a persistent memory region in NVMe. This isn't really the webcast to discuss that. There's other webcasts on that effort, but that's kind of where the bridge is. You're not going to get DRAM or DDR kind of latencies to a drive except through things like the persistent memory region.
Got it. So persistent memory DIMMs are usually addressed as memory, meaning byte addressable, and NVMe SSDs are usually addressed as storage, but so there are ways to address regions of the NVMe SSDs in a byte addressable manner as well. Correct. Okay, right, that's great, and I think that answers that question. Let me go ahead now and talk about one of the new options for NVMe over Fabrics, which is to run it over a fabric based on the TCP protocol. So first of all, there are many customers who like the NVMe over Fabrics because it increases flexibility. It, in some cases, increases efficiency of NVMe deployments because NVMe by itself is a way of accessing local flash storage or other non-volatile storage. It doesn't have to be flash. And NVMe over Fabrics lets you access that remotely. So you can use NVMe storage that's in a different machine or a different location by using NVMe over Fabrics. And so this is growing in popularity. There's more interest, there's more support from vendors, more customers testing it or deploying it. But there's some customers who don't want to build a special fabric. So NVMe over Fabrics first came out with support for RDMA, and then it added support for Fiber Channel. And so that's all fine and good. But there's some customers who said, I don't want to build a separate network, whether it's Fiber Channel or InfiniBand. I just don't want to build it. I want to keep my existing and use my existing network. There are other customers who are saying, well, I have Ethernet. I could use RDMA on Ethernet, which is either RoCE or iWarp as the actual transport, RDMA transport. But they're saying, I don't want to build a special, I don't want to modify my switch settings, or I don't want to deploy special NICs. Because to get good performance using RDMA, it runs over Ethernet, but you typically need special network cards or NICs. And for RoCE, which is the more popular RDMA over Ethernet option, you, at least in many cases, not always, but in many cases you have to make changes to the switch settings. And there are many customers who just don't want to make any of those changes. So these customers are looking for an NVMe over Fabric solution that runs on their existing networks. It doesn't require a new network. It doesn't require changes to their NICs or to their switch settings. And they want, so they want a solution that does this. In addition, it turns out that TCP, in most cases, scales farther in terms of distance than RDMA over Ethernet. So again, with RDMA over Ethernet, you can get some performance benefits, but there also may be more distance limitations because there's some latency restrictions, and if you go too far, then the latency gets too high and it becomes harder to use. So TCP has that distance, or that advantage in terms of distance scalability. So if we look at the different transport options that are supported for NVMe over fabrics, so first we have fiber channel. It's fast, it's lossless, it's very trusted and proven for block storage, but it does require a separate network. This is popular in enterprises, but it's pretty rare in hyperscalers, and very large data centers are, at least so far, pretty unlikely to use fiber channel SANs. InfiniBand is also fast, it's a lossless network, it supports RDMA, but again, you have to build a separate network. So you need a separate set of switches and adapters to run that. And InfiniBand is mostly in specialized networks for high-performance computing or artificial intelligence and machine learning. There are some cloud vendors and hyperscalers that have deployed InfiniBand, but again, it's not a part of their network that's usually doing something like high-performance computing or artificial intelligence. So Rocky over Ethernet, and the other RDMA option is called iWarp. These give you, fast performance. They're flexible in that they can run on your existing Ethernet network, but you almost always need special adapters, and you usually need to make some changes to the switch settings. TCP, on the other hand, and this is the newest one supported, it's everywhere, everyone uses it, it's already supported on all the networks. It doesn't have any special network requirements. So there was a question which I won't fully answer here, but of course you want, ideally, for using it for storage traffic and NVMe over fabrics, you want your network to be high performance, lots of bandwidth, low latency. So that's nice, but it's not required for NVMe over fabrics on TCP. You can use your standard Ethernet adapters and your existing switches, and you generally don't have to make any changes to those switches or those adapters to use it. So that's the big advantage of NVMe over fabrics on TCP. Let's talk about the actual transport. So it's designed to run over the IETF TCP transport, which again is ubiquitous. Pretty much everyone uses it and supports it and knows how to support it, all the vendors, all the customers. TCP provides a reliable, ordered byte stream between two IP endpoints. So at layer 3, you have IP, and then at layer 4, running on top of IP, you have TCP, which gives you that reliable and ordered byte stream running on top of IP. It's the same IP transport that's used by iSCSI, but you get the advantages of NVMe over fabrics, and NVMe over fabrics has certain advantages over iSCSI. They're both usually used for block storage. So the NVMe over TCP spec, or spec change, which is a change to the NVMe over fabrics 1.0 specification, it defines methods to allow the exchange of NVMe over fabrics capsules and command data over TCP byte stream connections. So the data is transported in capsules, and then you also have commands, and these both travel over TCP. So you have the administration and the I/O queue operations, as you can see here in the diagram, and these are both able to run over the TCP connection byte stream between the host and the storage subsystem. Okay, let's go to the next slide. NVMe over fabrics, or NVMe over TCP data plane usage. So again, we provide end-to-end NVMe IOQ operations on IP data center networks, where previously it had to be RDMA or fiber channel. Now it can run over the IP data center network. You have the NVMe over fabrics command and response capsule, as well as the command data exchanges. So again, the actual data transport is done in capsules with a command and response, and then you also have management commands that can run over this. So this is an alternative for block storage running on IP networks. Really, the only other option available for that is iSCSI, as we discussed. Other protocols either don't run over, other storage protocols either don't run over IP networks, or they're not for block storage. They're for file or object storage. So an interesting use case or an option is that the NVMe over fabric subsystem, which is usually the storage system, it has the option to provide support for NVMe over fabrics using both RDMA and TCP. And in fact, it can do that over the same network. Now, of course, it could also support both fiber channel and TCP, but that would be over, or InfiniBand and TCP, but that would be over two different networks running over in two different adapters in the storage subsystem. But when you use the NVMe over TCP, you're enabling both hosts. The hosts can connect to the storage with both RDMA and non-RDMA. So you have that option, and in fact, I believe at it was either last Flash Memory Summit or Persistent Memory Summit, I don't remember which, there was a vendor that was actually showing off a demo where they had a customer that connected to their storage system using NVMe over Fabrics, both with TCP and with RDMA, where they had the majority of the customers or the hosts connected with TCP because it's easier and more ubiquitous. And then they had a small minority of the hosts connecting with RDMA. Those that needed the highest performance were able to do that. But then they had to have the special network card. So host transport selection may be based on physical connectivity or on policy. So you can run it on two separate IP networks or on one IP network with different policy options. So from the specification standpoint, NVMe over TCP, it modifies NVMe over Fabrics version 1.0, and this is Technical Proposal 8000, or NVMe TP 8000. So those interested in details can look this up through the NVMeExpress.org website. It allows NVMe over Fabrics, again, to run on TCP, as we've talked about. It expands the transport options. So previously, again, you had RDMA, you had fiber channel. The RDMA could be Ethernet or InfiniBand, but now you also have TCP as an option. Now, customers who use TCP are in some cases willing to accept slower performance, but the performance can still be quite good. Testing so far has shown that it's usually a little bit slower than fiber channel or RDMA, but it's pretty close. So you can get good performance, and in most cases, for many of these hyperscalers, it's good enough, as well as being able to run up. Again, they don't have to make the network changes. The network, now this again relates to the question. So let me go ahead and cover this question. The question is, TCP still runs an IP Ethernet. IP Ethernet may show exponential backoff once you get past 70% network utilization. And it seems that solid-state transport, or solid-state drive transport using NVMe over Fabrics, one might expect to run high network utilization continuously, and not bursty traffic, which is what TCP/IP was originally designed for. So basically, the question is, how are you going to be comfortable using an Ethernet network that's used for maybe bursty traffic and less than 70% utilization when you have flash storage traffic, which might be lots of continuous streams and might be high utilization? So I think the full answer is beyond the scope of this webcast, but as I mentioned earlier, when you're using NVMe over TCP, you can certainly build a high bandwidth network. You can add extra connections. You have the option to make it a separate physical fabric. You can also you can over provision bandwidth, and you can also optimize the network to have better flow control or reduce congestion, or have better throughput and better quality of service. All those options are available and do work with NVMe over TCP. So you can, and in some cases maybe you should, optimize your TCP network or TCP fabric in order to support the storage traffic, but you have that choice because not all implementations of NVMe over Fabrics are going to fully saturate your network. Not all of them are going to be driving your network past 70% utilization. It really depends on the use case and the storage architecture. And I'll see if, Mark, I don't know if you want to comment more on that question before I go on. Okay, well, actually, Mark and I will both get a chance to address any other questions and comment more. So as we talked about, many customers want the ability to use their standard networking with no special hardware and something which scales farther in terms of both farther distance as well as the ability to run on a wider variety of switches and adapters. And NVMe over TCP fulfills that. And this was ratified, I believe, September of 2018, and it's available now. So that covers NVMe over TCP. And again, that's one of the several changes. Well, actually, let's dive right into the summary slide. So as we have shown and talked about, NVM Express, as an organization and as a set of specifications, continues to be responsive to hyperscaler requirements. So some of these very large customers, and hyperscalers often typically deploy thousands or tens of thousands of servers per quarter, and many tens of thousands per year, have come with specific requirements for different features or different use cases, and the NVMe organization has responded by updating the specifications or adding new features to the spec. These features are making their way into products now. So both the SSD vendors as well as many of the storage array makers or storage subsystem vendors and the ODMs are adding support for these new features that we talked about today. NVMe.org, NVMe-Express.org is going to be adding support for specific testing and certification of these new features in the runs regular plug fests and certification testing. Most of it is done through the University of New Hampshire Interoperability Lab, IOL. I'm not sure if all the testing is done through that, but much of it is. So as these new features are added to the specification, like in NVM Express 1.4, testing and certification of these features will be added as well into the interoperability testing. So you can find out more about these features, about these new specifications, and about vendors who are supporting these features if you attend Flash Memory Summit coming up in early August, or the Storage Developer Conference, which is a SNIA event that is typically in September. I think it's again September this year. So both of these events are great places to learn more about these new specifications, as well as the vendors and the particular implementations around them. If you have any specific questions about this webcast or about NVM Express, you can contact us at this address, nvme@nereus-worldwide.com. And of course, more information is available on the nvmexpress.org website. So now let's go to the questions. Megan, if I could turn it back to you to help us see what additional questions we might have.
Absolutely. So one of the first questions that we received is, what percentage of performance loss for NVMe over TCP what is it compared to NVMe over RDMA?
I would say it varies, and getting into the details might be beyond the scope of this webcast. But usually, from what we've seen from vendor demos and different vendors have done testing, is that it's slower, but it's not a lot slower. It's a little bit slower. I would say the performance difference could be, well, it's a wide range, so it's kind of hard to say, but maybe anywhere from 2% to 20% slower. But it really depends on, again, the setup and the network and the type of media and implementation of the storage subsystem. Mark, do you want to comment on that? Mark? Okay, I think Mark is on mute.
Sorry. Well, as regards to latency, there is some latency introduced by the TCP stack. Right? You got to marshal and unmarshal the capsules onto TCP packets. But throughput is probably not affected as long as you have enough processing power for that TCP IP stack. So you could probably get the same amount of throughput regardless of whether you're using RDMA or TCP. But the latency will be more, but it may be fine, maybe just enough.
Yeah, Mark, great answer. That's a good point, that actually the throughput shouldn't see any difference as long as you have enough networking capacity in CPU. So it's mainly as you said, mainly the latency that may be higher. But for many customers, it's, as you said, good enough.
Yep.
Next question, do we have any information on how NVMe over Fabrics is deployed in data centers like JBoss? They're also asking if we have any information on scalability.
I think that's a question for Mark.
Well, I don't think in most large data centers NVMe over Fabrics is deployed at this point. The systems that we've seen coming through, like Open Compute Project, hardware designs are largely attached via PCIe. So you can have multiple hosts attached to multiple drives through PCIe. They were waiting for the TCP form of NVMe over fabrics, but I haven't seen any actual system designs come out through OCP yet that would be able to take advantage of that. So, yeah, JBoss would really require the NVMe over fabrics to be implemented in the actual drive, and there's some indication that might be happening. But normally you're going to have a system that fronts PCIe SSDs with a bunch of networking interfaces, and that's going to be a more typical situation until the drives themselves get NVMe over fabrics implementations.
Great. Next question, why are hyperscale or data center requirements different from those of regular customers?
And by regular customers, you mean enterprise customers. Well, what happens is the typical enterprise storage vendors design systems with things like no single point of failure, more expensive, more featureful components, and as a result, they're just too expensive to deploy at such a large scale. And a lot of times the hyperscalers have software that's written above those components to make them more reliable, more serviceable, more observable, things like that. So the features that used to be down in the system for regular customers that don't want to deal with that have now moved up into software stacks running on very cheap commodity components, and the overall cost when you build a data center full of these things is much less. So the value that has typically been an enterprise storage value is not realized by these hyperscalers. So that's why they're pushing these requirements down into the drives, because that's what they buy. They buy drives. They build their own systems. They have their own software above that. And so that's why they're different.
Yeah, I would agree, and with what Mark said, and not only so in the end, because of their scale of operations, they tend to be more price sensitive, but they also have the ability to write their own storage software and apply that to the individual drives or the storage systems that they design, rather than having to buy and use software from a major storage systems vendor.
The next question is, what are the actual scale of NVMe over TCP and NVMe over RDMA deployment? What are the typical use cases of NVMe over fabrics with composable disaggregated architecture?
Yes. So what I've seen out there as sort of proposed designs would be to use NVMe over RDMA for everything in a single rack. It may also scale to a single pod. A pod might be a row of racks in the data center. So, it's a foot per nanosecond as far as latency is concerned. So you don't want to use RDMA for very far, because then it starts to break down. Whereas TCP is something that might be done by a top-of-rack switch that might convert the RDMA packets to TCP/IP packets for use with the rest of the data center. So that might be the breakdown. We'll see. And then none of this is deployed as yet, but that's the thinking so far, I think.
I would add to that for use cases. Oh, go ahead, Mark.
No, you go ahead.
Oh, so I would add that in terms of use cases, one use case we've seen is NVMe over fabrics to connect sort of a storage controller to a JBoF or basically a shelf full of NVMe storage. though that use case would probably be more in an enterprise storage system rather than in a hyperscaler, disaggregated solution. So we've definitely seen some storage vendors doing that, though again, that's more targeting the enterprise storage use case rather than the hyperscale data center. Definitely have seen some hyperscalers exploring or asking about or testing NVMe over fabrics as a type of disaggregation that's mentioned in the question. And so disaggregation being that they said the original design is each server has SAS or SATA flash, and then as it evolved, then each server started switching to NVMe flash. And then in some cases, they're saying that, well, I'd rather have a bunch of servers that share a storage subsystem, which is full of NVMe flash, and share it with NVMe over fabrics, either over RDMA or TCP. So I would say that's the disaggregated use case that I'm not sure I can say a lot of hyperscalers have deployed it today or in production, but I've definitely seen hyperscalers asking about it or testing it or exploring that idea, again, disaggregating the NVMe storage into centralized or into where a bunch of servers or hosts share one subsystem rather than each host having its own local NVMe storage.
Yeah, I'd say the disaggregated architecture is not fully bought in by the hyperscalers. I mean, somebody has to show them that it's going to be cheaper. Their major requirement is, I'm not going to pay extra for this, so show me that it can be cheaper.
That's absolutely true. At large scale, a small, very cost sensitive because a small change in the cost for one system gets amplified over tens of thousands of servers. So
right, yeah, there is work going on in something called computational storage, which would leverage the NVMe over fabrics to talk to not just storage devices, but accelerators and offload CPUs and compression, deduplication, those kind of features, being able to decompose those on the other end of NVMe over fabrics.
How easy is it to confirm the NVMe-oF resources in a data center?
I'm not sure what they mean by confirm in that question.
Right, me too. Yeah.
Maybe they mean to validate, like verify how much NVMe.
Maybe discover. But yeah, there's work to be done in discovery of NVMe over fabric resources. That's one of the things we punted on during the first release. But I would expect we're going to do more work in the area of discovering NVMe over fabrics endpoints and being able to connect those all together. So it's not easy right now. It's all proprietary, so work to be done.
Right, Mark, correct me if I'm wrong, but I believe today for discovery of NVMe resources has to be done fairly manually. Either the host has to have some idea or the host administrator has to have some idea of where those resources are, or the storage subsystem has to advertise them. And is that correct? That's the state of NVMe discovery today?
Yeah, and then on configuration, since that seems to be clarification, the NVMe over fabrics devices can be configured through the NVMe admin commands, which now also include the ability to send NVMe-MI commands in band over the fabrics interface. So they are easy to configure, as easy as PCIe drives.
Great. Well, that's all that we have time for, but thank you all for joining us. These slides will be posted on the NVMe website, and of course you can replay this webcast as soon as it concludes on the BrightTalk platform. Thank you all for joining us.